Welcome everybody to the Virtual Market Design Seminar. We are very happy to have Matt Jackson as today's speaker. He's professor of economics at Stanford University, and you might know his influential contributions to a broad range of topics, for example, mechanism and market design and political economy, among others. But in particular, his famous work on social and economic networks. Today, he will talk about how to design communication networks to improve social learning. Thanks to Matt for being here today, so early in the morning. And let me now quickly remind you of the procedures for the seminar. If you have a question, please raise your virtual hand or write your question down in the chat. In the next break, you can then post your question to Matt. If you prefer that I read your question for you, please write me a chat message. There will be some breaks during the talk and time to answer remaining questions after the talk. That's it from my side, and Matt, we very much look forward to your talk, and the floor is yours.
Thank you very much, Marianne. It's a pleasure to be here. So this is a joint project with Suraj, Malladi, and David McAdams, and I'll start with just a couple of quotes that sort of set the tone for this. So here's a quote from Elizabeth Warren saying that the safety of our democracy requires steps to fight disinformation on the part of companies. And then Mark Zuckerberg's retort that he didn't feel that Facebook or internet platforms in general should be arbiters of the truth. And I think we're in a point where it's clear that there are issues of information and how it's transmitted through platforms and other services that help connect people. And I think it would be nice if we can avoid censoring, and there's a number of reasons for it, but most basically platforms, crowdsourcing, governments, no matter how you go through this, there's going to be biases introduced in terms of what people's motivations are and what they end up censoring. It's also, there's a huge volume and it moves very quickly, and it's difficult to police, and algorithms have in general a pretty hard time assessing what is real information and what is satire, humor, or other kinds of things. So it's not easy to do. And I guess one question that we wanted to answer is whether or not it's possible to help design platforms to help ensure truth without policing its content. And so that's the question here. And just in terms of a preview, what we're going to talk about is learning when there's noise in a system. So when there's both misinformation and disinformation. So here there's going to be situations where people are either facing mutations in the information they're getting, or people who are deliberately trying to manipulate them. And the preview here is that effectively learning with noise requires hearing from exponentially many sources. So you're going to need a lot of different sources of information in order to learn. The second point that we'll make is that if information travels great distances and there's large volumes of it, then it's easy to have noise be sufficiently large that it's very hard for people to learn at all if they're not understanding how things mutate and what sorts of manipulations there are. And so the main thing we'll talk about is whether or not it's possible to trim the network in ways that can restore the learning properties. And I'll say just a few words about the literature. There's a fairly large literature on social learning and the difficulties in it. This paper sort of adds to that by introducing a model where there's noise in the signals as they're transmitted, and that noise builds up with distance. And so the further the distance is, the more the noise is. And so that's new to this literature, and effectively we'll be looking at in some cases some branching processes. Probably the most closely related parts out of computer science will be information theory. So we'll be talking about signal to noise ratios eventually, and there's some superficial relationship to birth-death models and evolution models. So let me start just with a little bit of motivation. And what I'm going to start with is an example of a paper from a paper by Levin, Noel, and Kleinberg more than a decade ago now. And what they were looking at was what chain letters looked like. And so this is a picture of a chain letter, and then sort of a blow up of it. So each one of these nodes is a person who then forwarded the emails, and then this sort of follows the chain of where these emails went. And in particular, there were effectively two that they analyzed, but the point of the picture here is that even though we have small world networks where people can reach each other, and you can get across the globe in 6 hops, when you actually look at the paths that these emails took, they were enormously long. And this tree is great in its size of depth relative to breadth. And in particular, the median node depth here is 288, and the width of the tree is only 82. So effectively, this is a very, very long tree, and most of the people, by the time this had reached them, it had traveled hundreds of steps. And when things travel these hundreds of steps, then it's quite easy for noise to build up. And in particular, I'll just give you an example from Malladi and a team at Facebook has been studying mutations. And here's one from one study they did. Here was a tweet: street style shooting in Oxford Circus for ASOS and Diet Coke. Let me know if you're around. So this is a message that was sent to tell people that there was an advertisement being filmed, and if you wanted to come to see that, here it is in Oxford Circus. And then that was misinterpreted, and it became, it was then tweeted within 3 minutes. It was tweeted, shooting in progress in Oxford Circus, what? And then shooting in progress, stay safe, people. And so the message was very quickly distorted and had a completely different content to what it originally had. And they've looked also at Facebook memes, and they looked at how these have been posted. And for instance, there was one that started, "No one should die because they cannot afford health care. No one should go broke because they get sick. If you agree, post this as your status for the rest of the day." It was posted more than 470,000 times, but the mutation rate was 11%. So about 1 in 10 times that it was posted with a different message than the original message. So people would stick in, no one should whatever, instead of "no one should die because they cannot afford healthcare." And so there was more, at the end, there was more than 100,000 variants. And they looked at 123 of the largest memes that had spread through Facebook, and 121 of them had more than 100,000 variants. So in general, this wasn't sort of an aberration, but when people were posting things, they were changing the content as it was being posted. And so the idea here is we're going to model situations where there's some content that's moving from person to person that is going to move in long chains, and noise can build up along the way. So the model is going to be, probably the simplest possible model you can imagine for this process. And so what we're looking at is there's a state of either 0 or 1, and there's learners who want to learn whether there's a 0 or 1. And they start with some prior probability theta that the state is 1. And there's going to be a bunch of people who see signals, and then they can send that out. They can broadcast that to their friends, and those can be passed along. And so we'll think of this as moving, say, on a platform from one person to another, and this message goes along. And the receiver eventually is going to hear signals via word of mouth, but word of mouth could be actual conversations, it could be emails, it could be postings, whatever. So this is traveling along through this process. And in particular, there's going to be mutation probabilities, and these probabilities, mu01 and mu10, are chances that the message moves from being a 0 to a 1. So somebody changes it from saying climate change is a problem to saying climate change is not a problem, or vice versa. And we'll take these to be IID probabilities. So they're going to be random probabilities that come along. And you can think of these as representing two things. One is that the message is either misinterpreted or posted in the wrong way, or that there's some people who deliberately try and change messages, and whenever they see a 0, they change it to a 1. So they only pass along 1s, or they only pass along 0s. Okay, so it could be random, it could be deliberate, but regardless of incentives. So here we're not going to model the incentives of the nodes to change the messages. We're just going to treat those as being independent. And those mutation rates are going to be what turns out to be important. So are there more people going from 0s to 1s, or from 1s to 0s? And this could represent, confusion being easier in one direction or the other, or deliberate misinformation happening one way or the other. Okay, and also we can have a different probability of passing a 1 compared to a 0. So we could have a probability P1 of a 1 coming along and you passing it along. So it could be that some information seems more important to you to pass along. This is new information, it was unexpected. And so you pass it with probability P1. 0s, it could be that you pass that with a different probability. So, funnier jokes, more salacious rumors, you pass them along with higher probabilities. Today, we're going to look at the case where these two probabilities are identical. So we're going to look at that special case. And in the paper, we talk about how you can learn from hearing things from long chains based on what these probabilities were. I'll say a little bit about that at the end. But I think all the points we can make in the case where these probabilities are identical. Okay, so essentially, let's think of the receiver being out there as the learner at the end. There's some original source, and it's being passed through this chain. And now we want to see what happens in this. And the model's then quite simple. If it starts out as a 1, so the original message was a 1, then there's some probability that gets passed along, and some probability that it doesn't mutate, so it stays as a 1. It gets to the next person. There's also a probability here that instead it ends up mutating and becomes a 0. And there's some probability that it's dropped. Okay, so it could either be a 1, 0, or drop. And you could also interpret dropping as the message was communicated in such a way that it was unintelligible. So I tell somebody something, but they just don't understand me, and that's as if it was dropped. So it either not sent or misinterpreted. It can drop. So then in the next period, then it passes along, and this is essentially a Markov chain. So a simple Markov chain where it's going from possibly a 1 to a 0. If it's a 0, it could go back to a 1. It could stay a 0. It could be dropped. And so these probabilities of mutation and dropping will determine what's the chance that as we move along this chain, if it's dropped, that's an absorbing state. It'll never be reappear. So dropping just kills the message. But otherwise, it can mutate back and forth between 0s and 1s. And so effectively, over time, there's some chance that by the time it gets to the final receiver, it's still a 1, still a 0, become a 0, or it's been dropped. Okay, so that's the basic model. Very, very simple. And effectively then, we'll just have T's we'll think of as time, but we can think of those as individuals, distances in this chain between the sender and the receiver. And then the Markov chain is just indicating there's a chance that a 1 is sent and it stays a 1, it goes to a 0, or it's becomes a null message, it's dropped. And that's an absorbing state. And so then there's a simple transition matrix, which is going to describe this. Okay, so that's the simplest possible model you can imagine of information transmission with noise. Okay, so let's talk about learning in this setting. So learning in this setting, effectively the receiver is seeing this, and we'll start with a receiver who's a Bayesian and can perfectly interpret these and realizes that there's a bunch of long chains, and think about them as, so imagine that there's, I'm sitting here and I'm getting long email chains. And so now I get to the end emails and I can read their content. And let's think of the receiver as seeing some number of different chains, and we'll consider chains of some length t, say 288, the median in that study. And then what's happening is as each t grows, each of these messages is going to be less and less informative. So by the time it gets to me, there's a good chance that it's mutated away from its original message or been dropped. And so I'll need a lot of these different chains in order to still learn, okay? And so what we'll think about is, okay, if I'm a Bayesian learner, I've got all these different chains coming to me, how many of them will I need in order to overcome the fact that these are mutating and changing and being dropped? And so I have a belief at the end that this state is 1 conditional on n of these chains reaching me or starting out, and then some of them will reach me and some won't, okay? Okay. So let's think of here's an example where P is 0.2, so there's a 20% chance that the message is passed, 80% chance it's dropped. And then say 0 moves to a 1 3% of the time, and a 1 moves to a 0 10% of the time. And so we start out with a 1. The chance that it stays a 1 is the chance that it's passed along times 1 minus the chance that it didn't mutate. So then we get a 0.18, right? So there's an 18% chance that I'm going to get a 1 by the first period, a 2% chance that it becomes a 0, and then an 80% chance that it's dropped. And so then you can just go through and you can say if I started with a 1, by the time I get to the second step, you can go through, figure out what the chance it gets there is 3% that it's still a 1, 0.007% that it's a 0, and so forth, right? So you can go through these calculations, and after 3, there's a pretty high chance it's dropped. And what's happening here is in the limit, the chance that I'm getting messages will look here like 0.2 to the t. This is gonna, the 0.03 and the 0.10 will tell you what the ergodic states of this, the long run distribution is going to look like. And here, effectively, you've got 3/13 of the time, it would be a 1 compared to a 0 is going to be 10/13 of the time. And then you've got a high chance that it's hit this absorbing state of being dropped. But the messages that do come through after long chains will be mostly 0s and some 1s. But the key here is that the effective learning is going to be done from the fact that it's got a slightly higher chance of being a 3/13 of being a 1. So it's approaching this 3/13 from above if it starts out as a 1, and a 10/13 from below as it starts out as a 0. Okay. So is that clear? If it started out as a 0 instead, the convergence would look very similar. The difference would be that it would reach this 3/13 from below and the 10/13 from above. Okay, so it would still converge to having roughly the same fraction of 1s and 0s because this thing would be mutating, but it would be a higher chance on being the 0 than the 1, and then the 1 chance, it's slightly higher chance of being a 1 than a 0. And so what's happening here is with many chains, or with long distance chains, you're going to have many of these to overcome the fact that most messages are dropped. So you need many just to make sure that you're getting through. And then you've got a relatively small differences of 1s versus 0s after long distances. So the longer this distance is, the more chains I need to overcome these relative mutation rates and to overcome the dropping rates. So that's the simple idea. It's just in the base model, and what we're going to start with is this, and then think about how to use this model to understand this learning problem, and then how to trim the tree. So we'll say that f of t is a threshold for learning if when the relative number compared to f of t of chains I have is large, then my beliefs are going to converge almost surely to 0 or 1. So I'm going to be able, as a Bayesian, I will learn completely. So my beliefs will be correct and I will understand what the state is. Or if the number of messages I see relative to f of t is small, then I'm going to get my belief being the original prior probability. So this is a threshold for learning means if you've got enough messages larger than this is the standard threshold in terms of a phase transition. If I have a larger number of messages, I'm going to be learning. Smaller number of messages, I'm going to be learning nothing. Okay, so that's the definition of a threshold. And then the first lemma is that if we've got positive probability of messages being passed along, dropped. And we have here we have the mutation probabilities. We'll keep them less than 1/2 so that this thing doesn't blink. But the threshold for learning then is just p to the minus t, 1 minus the sum of these mutation probabilities to the minus 2t. So it's quite simple formula, and that governs how many messages I would need to overcome. You can think of the first part as overcoming the dropping probability, and the second part as overcoming these mutation probabilities. And so if I have enough messages, and both of those are growing exponentially, so both of those grow exponentially in the length of the chains. So this, for instance, if p was the 0.2, 1 over p is 5 to the t. By the time you go in, 5 times, you're going to need thousands of these to make sure that they're getting through, and to make sure eventually that your mutations aren't being so large that you can't learn. Okay, so that's sort of the straw man, and the straw man sets up, if you had a perfect Bayesian and you knew exactly what this process was, then how many messages would you need in order to overcome the noise in the system? And then the next point is, and I guess, I don't know if we want to stop for questions along the way. Is there, I can ask for questions. If there are any questions, I'm happy to answer about the basic model. And now I'm going to go into what happens with unknown bias, and then we're going to start looking at how to overcome some of these noise. Okay, so no questions.
If you want to ask a question, just unmute yourself.
Yeah, I can't see the chat. So, so here, let's now think of the process when these mu's are not exactly known. And so there's some distribution over these, and I'm not sure exactly how often these things are moving from zeros to ones and zeros. And effectively here, if this is unknown, but has even, like some small connected support, then there's going to be imperfect learning. So regardless of how many of these chains you're going to see, the limit beliefs are going to be your prior belief. And what's going on here, I think the idea behind this is going to be fairly simple to understand. So let's think of what's happening in terms of this limit. So like in that example I showed you, we had this 3% chance of moving from a 0 to a 1, and a 10% chance of moving from a 1 to a 0. In that case, you saw that the limits were 3/13 and 10/13 as the relative probabilities of ones and zeros. Now, if instead you have a noisy channel where the chance of moving from 1 to 0 and 0, 1 are equally going back and forth, then instead of that limit probability being relative to 10 to 3, it would instead be 50-50, right? So this thing would converge to 1/2, 1/2. And what the problem is you're trying to make distinctions based on small differences in these relative probabilities, and differences in the mu's. So if you don't know what the mutation rates are, then that swamps the information. So you're trying to distinguish this by whether I'm getting slightly above or slightly below this threshold of, in this case, the 3/13 compared to 10/13. And so if I'm seeing slightly larger ratio of ones to zeros, then I think, oh, it must be state 1 because they're more likely to start out as ones. In the other case, it's more likely to be zeros. But now uncertainty about these mu's completely makes that, obscures that noise, because I'm not sure what that ratio should be. And I'm trying to make information off of small differences in these relative rates. And now I've got large uncertainty about that. Even small uncertainty about the mu's translates into large uncertainty about what that relative ratio is. Okay. And so that precludes learning. So basically here, limit learning from noise is very fragile. You're learning from slightly vanishing tilt of fractions of signals, and differences in bias and mutations non-trivially affects both of these. And so even small uncertainty about relative probabilities makes it impossible to learn. Okay. So we've got a fairly simple structure here where you've got messages being passed along. Think of this as like, Shannon entropy theory. So you've got a very simple setting, and now you're basically looking at the end you're looking at these messages, they're becoming increasingly noisy, so you need more and more of them to overcome the fact that each one of them becomes less informative. And slight information about how the system works makes it impossible to learn from the system. Okay. So now we're going to talk about optimal regulation and limits on the graph. And what I want to do is now take you through a very simple variation on this model where instead of only learning from these very, very long chains, we'll make this more realistic. And now there's going to be some messages that come to me from people close by, but there's also some messages that are reaching me from long distances. So when we look at that email chain, it could be that somebody directly, one of my friends starts the email chain and sends that to me. Or it could be somebody who 288 hops away started that chain. And same with memes. It could be one of my friends starts the meme and I get the original content about what the intended message was, but it also could be that somebody started it far away. And by the time it reaches me, it has I'm not getting the content, the original content at all. And this could happen with tweets or retweets, whatever you're looking at. And so we're both learning from near and far, and you don't know what the mutation rates are. And there's going to be effectively think of exponentially many sources far away. If this is a network structure, that more and more of the potential sources are going to be far from me than close to me, and we're going to take advantage of that. Looks like there's a hand up now, a question. Marco?
Yes, can you hear me?
Yeah.
So I want to ask, the probability that a message passes is always constant, right? And it is likely to believe that you can infer from long chains that the beliefs about the people before you, right? So can we adjust these, for instance, making that the probability that is the true state is higher if the chain is longer somehow?
Yeah. So in fact, what does happen is the probability that the message is true is exactly depends on that distance. So the further the distance is, and in the original, this sort of straw man model, we're assuming that the listener can actually see how many distances it's traveled. So you can see that listener knows how many points it's traveled, and then infers how many times it, what's the chance that it's still original state, and what's the chance that it's mutated to some other state.
I see.
More generally, you can think about, so this is assuming that everything's IID in this system. It could be that over time, if that you begin to learn, I know you're on Facebook or LinkedIn or Twitter, whatever platform you're on, and you're getting messages, you realize that from some people, the messages are a lot noisier than from other people. So in the particular model we're looking at, where the listener is treating every potential source as an IID source and knows those distances and is building up. So if things have come to me a distance of 3, I realize that there's a pretty high chance that they're true. If it comes to me from a distance of 100, then it's much less likely to be true. And so in the original model, knowing those distances and knowing exactly how it's traveled, I can begin to unravel that. We don't allow the listener to have different nodes, have different probabilities, and be learning that over time, which in fact most of us usually do, right? So there's some people we trust more, and we think that information that comes through them is higher fidelity than other people.
Thank you.
Okay, so now what we're doing is in that original model, you've got a known long distance that we're looking at, and long distance learning becomes hard as the distance increases. But now what we're going to be doing is learning from close and far. And so think of this as I'm this node at the bottom of this tree. So there's messages coming in through me. So think of the network, my network going out. I have friends of friends, friends of friends of friends, and so forth. So that explodes exponentially, right? And if you're looking at something like Facebook, where typical average number of friends is in the order of 500, then this explodes as 500, 500 squared, 500 cubed, and so forth. And there can be sources at any distance, right? So any of these people could be a source of a message. So these could be people that have read an important article that they want to communicate, they want to post that, they post a message about it, and then that information is coming to me, okay? And so what's going to happen is as this tree expands, there's a higher and higher chance that there's more of the nodes at greater distances are going to be sources, right? So when I think of original sources of messages, I've got 500 friends, I've got 500 squared, 25,000 friends of friends, and then so forth. There's going to be a higher chance that the messages are going to be coming from further and further distances. But now I'm going to be learning from all these messages. So these messages are coming in, I see them, and then I'm trying to disentangle them. Okay. And so if we think about the ratio of far to near, if you want to think about some distance t compared to some big T compared to some smaller distance, little t, the ratio of how many nodes are at that distance is effectively in terms of information passing is going to be dependent on what's my effective degree. And you can think of this like a reproduction number now that we all have started learning about reproduction numbers in graphs. This is essentially the reproduction number of this tree. P is the probability that a message gets passed, and D is the number of connections on average. So think of D as my 500 friends, and then P is the 1/5 chance that one of them passes things along. That means that I've got like 100 effective friends. And then, as you go out, then you think of how this expands, and this gives you the expansion rate of this graph. Okay, so this is sort of the expansion rate, and then how many nodes at different distances are is just going to depend on what this is comparing different distances. And so what's happening here is that in terms of the size of this tree, there's increasingly large numbers of nodes at greater distances, and then smaller numbers of nodes, relatively smaller numbers of nodes at smaller distances. Okay. So what's the issue here? Effectively, the long distance nodes are going to be very hard to learn from because there's going to be so much noise building up by the time that their messages get to me. Whereas the close by nodes are going to have higher fidelity. Those are going to have fewer mutations. And so in order to restore learning in the kind of environment we had, what we'd like to do is somehow trim this tree to control the structure of the tree of the far distance nodes compared to the close by nodes. So think of now information's originating from any node, and we're going to think of an individual, think of their expansion structure as like a tree. So we're not going to allow cycles in the graph just for tractability reasons, but you can throw in cycles, and then it just allows messages to travel multiple paths, and so then you have to disentangle messages from multiple different paths. Again, we're going to stick with this probabilities being equal of passing messages along. And more generally, what this begins to, the case that we treat in the paper where these probabilities are unequal, what that adds to this is just that, if I hear a lot of information, if I hear a lot of buzz about something, then maybe I think, oh, this must be a 1 because otherwise people wouldn't be talking about it. And so, I infer just from the number of messages I'm getting that something about the state. And we show that effectively you get similar kinds of results whether or not you're thinking about just counting the number of messages or counting the relative ones versus zeros. A Bayesian can make use of both of those, and one of them is going to dominate in the end. But for the purposes of the talk, we'll just again stick with the P0 equals P1 case. And now we've got these different mutation rates, and I'm going to suppose that they differ and they're unknown. And we're going to start with take the receiver to have a symmetric prior over the state and these zeros and ones. So what the receiver is going to do is basically just go with a majority of signals. So if I get more ones than zeros, I'm going to believe 1. If I get more zeros than ones, I'm going to believe 0. And so what we want is, we want robust learning in the sense that we want the tree to be structured so that the majority is going to be correct in expectation. So in expectation, regardless of whether it starts out as ones or starts out as zeros, we'd like the majority of the messages that reach somebody to be correct. Okay, so to learn from these both near and far, what we need to do is improve the ratio of near to far. And we can trim the tree in two different ways. We can limit the depth. We can say, look, we're not going to allow messages to travel more than 10 times. So we'll just, set an arbitrary distance. And once a message, if we're the platform designers and we can see that a message has been transmitted 10 times, then we're going to stop it and say it doesn't go any further. You can't transmit messages any longer. The alternative is to do what WhatsApp and Facebook have actually done, which is to limit the breadth. So you're not allowed to forward these messages to more than, say, 5 people. So 5 is the cap that they've used. And they can say, okay, in the case of WhatsApp, it's actually encrypted. So they're not quite sure what's being sent, but they can just say, you can't send this out to more than 5 people. So you pick your 5 people and then send it along. And that's, instead of limiting the depth of the tree, that's limiting the breadth of the tree. And part of the reason for doing that is that they might not be able to check which messages have been sent multiple times. So for some platforms, it's actually impossible for them to check, if it's encrypted, for them to check whether it's the same message going along. So what they can do is they can limit the breadth instead of the depth. Okay, and so we're going to talk through what the advantages of each one of these are. So when we go back to our example, after 3 steps, most of these were true still. So the ones that were coming through, most of the messages dropped. But if we had lots of sources starting this out, if they were only traveling distance 3, most of them would still be true. So it'd be like a 3-to-1 ratio of true to false messages if they only traveled a distance of 3. So for these particular numbers, mu01 and mu10, we could ask, when is it, if the state starts out as a 1, there's actually a higher chance that it's going to change from a 1 to a 0 than from a 0 to a 1, right? So there's a 10 to 3 difference in these mutation rates. So more often it's going to be going from 1s to 0s than from 0s to 1s. So eventually that's going to flip. So after a distance 3, you've still got most of these messages being true. But if you, in this particular case, most of them are false eventually in the limit. And you could ask, how many times does it have to go before it flips from being mostly true to mostly false? And for those particular numbers, this changes after 7. So for 7 iterations, you've still got a higher probability that it's the true state. And then at the 8th iteration, you've got a higher chance that it's the false state than the true state, okay? And so what you can do is you can do a calculation as a function of these mu's of what's the distance after which the messages have flipped from being mostly true to being mostly false in the state where it's mutating away from that state with a higher probability. So is that idea clear? Okay, so eventually this is going to flip over and because the mutations become false. And so what we can do is say, you can cap, if you wanted most messages to be correct, you can just do a calculation of when that flipping point is. So you can there's some Markov chains, so you can go through and do the math. You can calculate after how many steps is this more likely to have transitioned from 1 to 0 than back. And in this case, that t is a function of these mutation rates, and this is the particular exact formula of what that looks like. And so when we went, with that case, the bias in the previous example was towards 0. So if the true state is 0, that's no problem. Things are mostly moving towards zeros. But if the true state is 1, messages that travel too far are more likely to be false. And 7.5 is that threshold. So after 7.5 iterations, then you're more likely to have the messages have flipped. Okay. Okay. So now let's think, if I can't cap the distance, then what I can try and do is ensure that more messages are coming from close to far. So one possibility is I just look at this thing and I say, look, messages that have gone more than 7 times are more likely to be misleading. So if I'm the message, the platform designer, and I can, check these mutation rates and see what the tree looks like and so forth, I could just cap this at 7.5. But if for some reason I can't see that, I can't see into it, and I don't want to cap the tree, then instead I can also cap the breadth. And that's something that's easier to do for the platforms. And so let's talk through the breadth capping. And so instead I'm going to cap how many people you can forward things to. And as the breadth of the tree increases, you get exponentially more nodes at further distances compared to up close. And so cutting the breadth also improves the ratio of near to far and the signal to noise ratio. So let's just go through a picture of this. So, one possibility is we go through and we cut things in this tree. We could say, look, I want most of this stuff to be close to you. I'm just going to cut it at distance 3. And then those large numbers of messages that are coming from further away that are going to be noisier and confusing, we'll get rid of those ones. And the ones that are more likely not to have mutated, those will leave. Okay, so we can't do that. How can we control this? Because this is growing exponentially. One possibility is instead of capping that distance, we're just going to cap how wide this tree is. So we just chop off and we say, look, you can only send this to 1.5 friends on average instead of 2, right? So this tree was drawn with 2 just for obvious purposes of the drawing. But we could limit it to be less wide, and capping it to be less wide would also increase the ratio of close by messages to far away messages. So I can either limit the distance, or I could limit the width of this tree and say how many people you can be sending messages off to. And if we cap that breadth, that's another way to improve the ratio of near to far. Okay. And so what we'll look at is, let's suppose that you haven't been able to bound the T at all. So you've got these trees where messages could be originating at any distance. And we'll look at Galton-Watson processes. So these are simple branching processes that, just think of a random tree where if the degree is 500, I'm going to get IID draws of like a Poisson distribution with 500 of how many people I have, and then next and so forth. So think of a random tree. Then you look at the expected number of true messages. That's going to exceed the expected number of false messages in both states, if and only if the breadth of this tree is bounded by 1 minus 2 times the max of the mutation rates divided by 1 minus the sum of the mutation rates. So it turns out to be a very simple formula, which actually governs it's a remarkably simple formula, in fact. We didn't expect it to be this simple, but it turns out to be an exceptionally simple formula, which gives you the bound on when it is that you have a higher expected number of true messages than an expected number of false messages. And if things travel farther than this, then you expect things to be to have mutated. Okay. So is any questions just about that proposition? Okay, so we have a bound on the breadth, and so this says that if PD is less than this, then you've got the learner can learn, at least on average, there's going to be most of the messages is going to be true rather than false. And you can see 2 quick things about this formula. First of all, this is decreasing in P. And so here, having messages be sent along with higher probability is actually damaging for the learner. So the higher the chance that people forward messages means that there's a higher and higher chance that things are coming from greater distances and a less of a chance that they're coming from short distances. And greater distances have more chance of mutating. And so the higher this probability that things are sent along means that then I have to have a tighter and tighter cap. And so this is decreasing in P. So the D I can use is decreasing in P. It's also decreasing in the max mutation rate. So the bigger the mutation rate in the state that it moves away from with higher probability, that means I have to have more constraint. And it's increasing in the min rate. So basically, the closer these 2 mutation rates are to each other, then I have to worry less. The case where you really have to worry a lot is when there's a distortion in one direction versus the other. That people are really distorting things, say deliberately, from 0s to 1s rather than from 1s to 0s. And if that's the case, then you've got a problem in terms of the learning. And so the bigger that difference in mutation rates, the bigger the problem. Okay. So again, if you go through this, if you had these probabilities that we've been using in this running example, then the cap on the T is 7.5. But if you can't cap that T, then the cap on D turns out to be 4.6. So what you would want to do is you would want to limit the breadth of these messages to 4.6. And WhatsApp and Facebook recently capped WhatsApp did it about 2.5 years ago. Facebook did it last year, where they capped forwarding messages at 5. And so that would be, roughly what you would want. If these were the numbers, you would want to cap the D at 4.6 to make sure that more messages were still truthful rather than having mutated to false. Okay, one point here, if these mutation rates are different by a lot, so if there's a real asymmetry in the way that these things mutate and P is large, then it's impossible to satisfy. So there's no way to do this if you're basically just stuck and the learners aren't going to be able to learn anything if there's a high probability that messages are passed along. Even if you trim it all the way down to a breadth of 1, then you're not really going to be able to satisfy this. So many messages are coming from far and likely to be false. In that case, there's nothing you can do. Okay, last question here then. The cap ensures that there's more correct than incorrect messages. And what if we want to maximize the difference? So the cap just made sure that was the distance at which they're going to be more likely to still be true than false. But in fact, that doesn't maximize the probability that they're true rather than false. So instead, we could say, look, if I even shrink the cap further, so there's one point at which they're, I'm making sure they're more than true than false, but I could maximize the probability that the messages, that there's more true than false messages. And so here, the expected number of true minus false messages is maximized at this particular degree. So you can calculate what that degree looks like. And this formula is a little more complicated than the other formula, but it's still relatively simple, and it works out in it has the same kind of comparative statics as the cap expression, but it's going to be a smaller number than the cap. So you're going to have a smaller cap if you want to maximize the expected number of true minus false. So for instance, the cap, you work out what the caps would be. The maximizing D here would be 1.8. If in that example, if you change that P to 0.1, then you double this to 3.6. If you took it to 0.05, you'd put it up by a factor of 4 to 7.2. So you can go through what these calculations are. But in this case, the cap is a little more than a third. So the maximizing D is about a third of what the cap would be. And so again, depending on these, you can go through different numbers and calculate this. And this is just, obviously these are a highly stylized example in terms of this model, but it captures this basic idea that there's some mutations, there's dropping probabilities, and controlling the size of this tree is going to help. Okay, so just in summary here, we've got the simplest possible model we could think of to allow for misinformation and disinformation and dropping messages. And so we added this noise. And the first simple point is, okay, if I'm a full Bayesian and I really understand and I know what these rates are, I'd need many, many messages, sort of an exponential number to learn. But slight uncertainty in mutation kills that ability for even a Bayesian to learn. And so in this setting, then crude simple caps on the size of the tree can restore learning and make partial learning possible. So it can be sure that even very simple naive learners that are just following a majority of messages will be getting majority of messages that are more likely to be true than false if you just limit the tree. So you either cut the distances, or if you can't cut the distances, you cut the breadth of the tree. Okay, just some final thoughts then. So, I think part of the reason for doing this is that the learning literature has focused, like the DeGroote learning literature, as I've been working on, and other people have been working on various herding and Bayesian kinds of models in these worlds. You can work with whatever model you like, but most of those models assume that the messages are sent without distortion in them. And when you start working with distortion in these things, the noise quickly builds up, even with small probabilities, given the exponential structure of networks. And so that introduces a big problem in learning. And that means that you're going to learn from shorter chains rather than further chains. And I think one sort of interesting aspect that this points to that I think sort of an important next step in this kind of modeling would be that, okay, we want to structure these networks to be small. So we want to cut the distances in these things, and we want to limit how expansive the networks are. But that could also drive polarization. So to the extent that now people are only listening to people that are close by, and this could also be true even if if you're in a human network, not mediated by a platform, so not a designed platform, but even if you're trying to do this yourself, you only trust things that you know came from people close to you, then the only information you're going to be getting is from people close to you. And so if people are only learning from people close to themselves, then if those people close to themselves are similar to themselves, they're not going to be getting very diverse information. So in this, in the simple model we had, every node could be an equally likely an original source of valuable information. But in fact, in many of our networks that are in practice, in application, it would be true that there might be biases in the sense of I might have more access to information about zeros than ones, or vice versa, depending on my type. So if there's certain demographics and certain kinds of people are going to have access to certain kinds of information, then trimming these trees can actually, be problematic and it can sort of drive polarization. So then you can get to a point where you're sort of stuck either not having any learning at all or having polarized learning. And so I think, there's a lot that we should be understanding about the fact that people have incentives to misrepresent information, to distort information, that information gets noisily transmitted, and that people are trying to aggregate this in fairly complex systems, and that limits their ability to do so. So I'm happy to take more questions and have any discussion of points you want to talk about. Thank you very much.
Hi, man, this is Peter Crampton. So one very broad question that I have is, can you point to some examples like Wikipedia, where we do have some learning, especially Wikipedia, say in mathematics. I can go to that and I can pretty much trust what's there. And they have a particular policy. I don't actually know what it is, but are there examples like that you can point to where there's sort of success in developing networks of trust?
Wikipedia is sort of, I think, one of the most amazing examples. I think it's the most unexpected example I could imagine in terms of how well it works and how both how well populated topics are. So, as you're pointing out, if I want a theorem in mathematics, then it's easy to find most questions you want, and they tend to be correct. And Wikipedia, I think there's three things that are different about Wikipedia than this model. One is that it's curated. So they actually do go through and they have a complex system of editors, and editors earn credits and so forth, and they police this and they go through and they edit things. The second is that something like mathematics is relatively uncontroversial. It's not as if people are trying to distort you and get you to not understand some Kolmogorov results from so it's not that they have incentives. So the mutation rate is going to be relatively low. Those mu's are going to be only because the person entering the thing really made a simple mathematical mistake, and most of the people editing there don't tend to make those. So they get corrected also by the editors. But I think so. It's fairly special. They have a lot harder time on, if you wanted to look up Palestine-Israel conflict or something, those pages are constantly in flux now and full of stuff that goes in and it goes out and gets chopped. And so it's probably a less good source for that kind of information, where there's going to be high mutation rates, high relative ideas of trying to distort the message one way or the other. And so I think things that are more controversial, they have more problems with. And also, I think, we're looking at a place where these messages, I think if you look at the halftime, for instance, on Twitter, most of tweets and retweets happen in an 18-hour window, right? So it's like the half-life of most Twitter feeds is literally 18 hours where all the action happens. And when you look at Wikipedia, it might be months or years, where these pages evolve and eventually gain content and it becomes more curated. And so I think that part of the difficulty is that, we're thinking of really fast moving systems where you might want, information to spread fairly quickly. And in that case, it's going to be much more difficult to actually have editors that go through and curate all this. And also it's just the labor amount of time for doing that is enormous. And Wikipedia now is starting to hit its, it's more difficult to get people to still want to be part of that community and still doing it. So it's more difficult for them to do that now. But I think it's good. It's a great example to say this model is a very narrow niche in terms of, we took an extreme model of one part of this large ecosystem, and there are ways to sort of make curation and moderation work. But this is, trying to do the best we can without that. And so that's, I think there's a whole spectrum of things that we'd like to understand better in terms of that noise. But Wikipedia is an amazing example. Yeah, Marco?
Hi, yeah, this is very interesting. And well, I guess I have two questions. So one is like how bad is it if the T is unknown compared to like a certain rate of mutation? And my second question would be, so if you like here, essentially you're assuming that, well, if you don't receive any information, that's more or less okay because you're looking only at the whether you receive like a majority of like one or like the other signal. But if you don't receive like it, I guess there are situations where it's essential to receive one type of information and it's not so bad if you don't receive another type of information. So I was wondering how that changes your results on regulation, I guess.
Yeah. So let me take the second question first. So here we haven't really put in an objective function on sort of the cost of having most people believe zero and then having important ones be dropped compared to the other way around. And so what that would do is, I think, adjust a lot of these formulas. So the formulas now are symmetric effectively in the zeros and ones in everything we did there. And if you have, if you want really important information to get through, say, the vaccine works and that information is more important to get through than the vaccine doesn't work, then you would want to distort these things in certain directions that depend on the relative mutation rates from that state to the other one. So I think it would make an adjustment. So you could put in a weighting on the importance of the states, and then that would weight those mutation rates effectively in all the calculations we did. The not knowing the distance. So, in the second part of the talk, more or less, the problem is that people can't see distances. I think one thing that's interesting and one thing that I do much more than I used to now that I've worked in networks is I look for tags on information. So information that you can't tag, and what do I mean by tag? I mean, tell where it came from. So what's the original source and how far has it traveled, and what are the chances that it mutated before it. So if you talk to somebody in person, you can ask them, well, where did you actually see that, or where? And if you say, well, I'm not sure, I don't remember, then you put less, credence on that than somebody who says, oh yeah, and I read this yesterday here, and then you can go check that and see where it originated from. So seeing the distances that things have traveled is very important, and I think it means that platforms, another thing that we did not consider would be the ability of platforms to put tags on things and say, this is a message that traveled 3, this is a message that traveled 5, and this is a message that came, from 7, and so forth. And if I could begin to see those distances along with the messages, that would help the end user a lot in sort of untangling that. And I think things like Twitter and other kinds of things, you have a little more ability to sort of trace back. That can be undone, but platforms that have that ability, you have a little more idea of where it originated from and what the veracity can be in that case.
Thanks a lot.
Yep.
Matt, let me ask you a quick question. In general, if I looked at a tree at any point in time, I might be able to go back and identify forwards of messages that look like they were mutations. And if I did that, in principle, I could go back and look at the history, identify things that look like they're more likely to be mutations, and block forwarding of them.
Yes, yeah. So I think, you know, platforms can begin to police, and to the extent, so what we're doing is putting a pretty strong block to say it's impossible for platforms to look into and have an idea of whether zeros or ones are true or false. So they're not going to do that at all. But you're right. If you know, if you're able to see mutation rates, and you can see nodes that are high mutation rates or high bias, that they're always moving zeros to ones, then that would be something you want to block. And so, you know, I think part of the difficulty for platforms in doing that, especially with deliberate misinformation, is that now people who are interested in doing that are fairly good at creating false accounts and starting new accounts, and, you know, putting in new users that then generate things. So then you're playing a game of catch up. But that would be another thing to do, which is, you know, to the extent that you can police the messages and you trust whoever's policing the messages, then you want to do that. I think the difficulty is that, you know, with whatever platform, if it has any bias from zeros to ones or ones to zeros, you could imagine that it somehow polices things more, you know, more in one direction than another, and starts censoring in ways that we don't want that to be done. But you're right. In here, as a person, you would want to be able to identify, look, this person seems to always send me ones, right? I'm no longer going to listen to them. If everything, the message that comes out of them is always a one, then you know, that there's some bias there, and I won't trust them anymore. And the platform can do that as well. Thank you very much, everybody.
Are there no further questions? Now there's the last chance to ask. Okay, then thanks a lot, Matt, for sharing all your thoughts and results with us, and thank everybody for your participation. We hope to see you again in 2 weeks when we have the pleasure to welcome Martina Rostek in our seminar.